Men did not understand what is fire until it burnt him. He did not understand what is water until it drowned him. Neither did he understand the impact of money until he begged for it. The civilization did not understand the significance of waste until it got poisoned by it. Ladies and gentlemen, I present to you today perhaps the most premier issue of waste handling which has been perturbing human civilization since decades together, the handling of blast furnace slag, brought to you by myself, Alomai Banerjee, third year mechanical engineering. Wishing a very good morning to all my dear guests out here. Let us begin this presentation. Now coming to a brief outline of the topics that will be covered in today's presentation. First, we will classify the various varieties of steel slag that are available in blast furnace slag treatment. Next, we will move on to the process flowchart which will be followed in today's presentation. Obviously, it will be followed by the description of each of the sub-processes of the process flowchart. And finally, we will conclude with a real-time case study performed on the following topic. Now first let us classify the various varieties of blast furnace slag. First we have air-cooled slag. As the name suggests, the slag treatment is done in a pit in atmospheric weather conditions and it is allowed to cool in atmospheric air in the absence of any cooling agent. Next, we move on to something known as granulated slag, where the cooling is accelerated by the presence of water. Then we have expanded slag, where cooling is done by a combination of water and steam, which results in the development of a foamy structure of less bulk density. Granulated slag can be further classified into three subdivisions. Pit granulation, where the blast furnace slag is actually led into a pit filled with water. Jet granulation, where we not only exert the cooling effect of water, but what we also do is that we exert the pressure of the jets in order to cool the blast furnace slag. And we have dry granulation, where we have the cooling taking place in absence of adequate quantity of water. Now this is the brief process flowchart that will be followed in today's presentation. Ladies and gentlemen, let us make it very clear that this is not a new process that we are talking about. This is a process which has been followed since as early as 1830s. In England, the first blast furnace slag was used as a construction aggregate. But the problem with this process is wherever this has been used, in 2 to 3 decades there has been failure of the constructed pavement or road. So we aim at providing a process flowchart which will ultimately give a pavement or a road where there will be minimization of scope of failure. First, this blast furnace slag, as you can see, is coming out of the slag knot and is led into a pit. As I said previously, since the cooling is taking place in atmospheric weather conditions in absence of any cooling agent, there is proper time for the development of crystals as well as prominent grain boundary. This gives the slag a rugged topography which is absolutely essential for the carrying of dynamic load in pavements and construction roads. Here the second point, you can see that the cooling rate will be accelerated by water, but as long as it is not affecting the grain boundary structure or the crystal structure of the slag, we can use water as a cooling agent to accelerate the cooling rate. Now the moment this blast furnace slag is coming in contact with atmospheric weather conditions or water, there is emission of huge amount of volatile matter along with something known as hydrogen sulfide. Hydrogen sulfide, prospectively speaking, is one of the most severe threats to our environment and one of the most severe issues that need to be dealt with while we are handling steel plants is that we have to eliminate or minimize hydrogen sulfide generation. What we use as anti-emission agents is aluminium oxide, calcium oxide and sodium carbonate. What they do is they act as soluble bases in order to neutralize the acidic effect of hydrogen sulfide. Here the data, as you can see, 95 to 98% H2S removal is actually possible if we are including 3% of anti-emission agent in the cooling water which we are using in order to cool the blast furnace slag. This picture you are seeing is not any random explosion which is taking place. It is basically blast furnace slag coming in contact with atmospheric water which is generating huge amount of H2S and volatile matter that you can see on the slide. Next, we have treated the blast furnace slag with something known as alkali in order to neutralize the acidic effect of H2S. But the excess alkali needs to be removed because if it is not removed, what it does is alkali-silica reactivity, leading to one of the major causes of failure of the blast furnace slag in construction pavements. That is why we are using class F fly ash. The calcium oxide content of the class F fly ash is primarily responsible for neutralizing or consuming the excess alkali that is present while we are using anti-emission agents in order to reduce the generation of H2S. Now, one thing needs to be mentioned in this regard. Class F fly ash is pozzolanic in nature, that is, it does not have any self-cementitious properties. It acquires adhesive properties in presence of water and concrete. Whereas on the other hand, we have something known as class C fly ash, which is actually having self-cementitious properties, having more calcium oxide. But the primary problem with class C fly ash is that it has huge amount of sulfates. And sulfur is one of the major causing agents of failure in construction pavements. So we are using class F fly ash as treatment in order to neutralize or consume the excess alkali present. Next, we move on to the iron unsoundness test. This is caused by the partially reduced oxides if they are present in the blast furnace slag. Practically speaking, they actually are observed in blast furnace slag which have been stacked for a long time. If we go for a constituent analysis of the slag, steel slag, which is actually experiencing this iron unsoundness, it has 3% ferrous oxide and 1% sulfur. It is prone to iron unsoundness test. The question is, how do we remove it? We actually keep the slag immersed in water for 14 days, within which the disintegration actually takes place. Once the disintegration takes place, we can use it in the construction of the concrete pavements. Next, we move on to the dicalcium silicate unsoundness test. Now the question is, as long as the slag cooling is taking place, this dicalcium silicate is actually converting from beta to gamma form. That is, in the hot slag we have the dicalcium silicate in the beta form and it is getting to gamma form, and it is common knowledge that as long as this phase change is taking place, there will be a volume change. This volume change before cooling, if it is included into the concrete pavement structure, what it does is it generates unwanted stress concentrations in the concrete structure, resulting in ultimate failure of the concrete pavement or road we are concerned with. Next, we move on to the calcium sulfide ettringite formation. This calcium source is actually the flux of limestone which is used in the blast furnace slag. This calcium sulfide actually, again as I said, this sulfur is one of the major contents or major issues behind the failure of the concrete pavements or roads. This calcium sulfide on hydration produces this complex compound whose chemical formula you can see on the screen, which is known as calcium sulfide ettringite. What it does is it compromises the air void spaces or the intermolecular spaces which are present inside the concrete pavement structure. In places where you can see something known as freeze-thaw damage out here. In places where the temperature in harsh winter conditions falls below 0 degrees Celsius, the moisture in the intermolecular spaces freezes. Freezes, there is expansive force generated on the intermicrostructural level. As there is expansive force generated, there should be air gaps in order to account for the allowance of these expansive forces. But if there is calcium sulfide ettringite formation, what it does is it actually shuts off the air gaps or the air voids which are at present, which should have been present in the microstructure, thus resulting again in unwanted stress concentration, resulting in failure of the concrete pavement. This is the most important issue when it comes to the handling of blast furnace slag in construction aggregate, because we cannot keep the moisture content on either side of the optimum level. If the moisture content is kept more, what it does is on freezing, it actually generates again expansive forces. As I said in the freeze-thaw failure part, it generates expansive forces resulting in the failure of the concrete structure. And if the moisture content is low, what it does is absence of hydrolubrication. As hydrolubrication is absent, it again leads to the breakage or the failure of the concrete structure, which is common knowledge for any concrete structure. If hydrolubrication is absent, there is failure or scope of failure of the concrete structure. Now I have given you a flow chart which will analyze the processes which will take care of all the failures. But there has to be a reality check, a real-time case study which will ultimately prove that the flow chart I illustrated, the process flow chart, is actually real, is actually prevalent in the real world. This is the data which has been taken from a case study which has been carried out by the Michigan Concrete Pavement Association in July 2006. 3 countries are in observation here. As you can see, Wayne, Oakland and Mocambo. Here are the street names and the year of construction of the pavements. You can see actually the tests are being carried out, the observations are being carried out 1 to 2 decades after the construction of these pavements, and each of these pavements have experienced failure after the use of blast furnace slag as steel aggregate. So let us analyze the causes of failure as has been given by the MCPA report in July 2006. The first cause is the alkali silica reactivity. As I said, in order to remove H2S, we needed to use alkali in order to neutralize the acidic effect of H2S. But in this case, there was no class F fly ash that was used in order to consume the excess alkali. And as there was no consumption of excess alkali, the ultimate solution became prone to the alkali silica reactivity, resulting in those defects as you can see in the microstructure. This is an image which has been given by the MCPA of the microstructural failure of the concrete pavements. Next, as I said, in southeast Michigan, the temperature ranges on both sides of the 0 point. In harsh winter conditions, it falls below 0. And there was no allowance for the expansive forces that were generated when water freezed. And that is exactly what happened, resulting in the discrepancy in the air gap, no allowance, leading to failure of the structure. Next, we follow it up with the ettringite formation, where we have again the excess sulfur content, as I mentioned to begin my presentation. The excess sulfur content leading to ettringite formation, compromising the air void spaces, and as the air void spaces are being compromised, the freeze-thaw failure is again coming into the scenario. Then last is, as I said, the hydrolubrication part. The hydrolubrication part, if the high water cement ratio is greater than 0.5, it resulted in extra moisture creeping into the joints, freezing into ice particles, and thus resulting in expansive forces to be generated. These are the reference materials which I have actually referred to in order to generate this paper. Ladies and gentlemen, it is a common question which may arise that I have given you so many efforts, so many processes, so many chemical tests in order to use blast furnace slag as a concrete aggregate. But the question is, why should we use blast furnace slag as a concrete aggregate if it is prone to so much failure? The question is, blast furnace slag is one of the most difficult waste handling that is addressed in the industries, and construction industry is one important points where we can dispose of this blast furnace slag both environmental friendly and recycle friendly. And that is exactly the issue that has been tried to be addressed in today's presentation. Thank you.
I have one more question. The question is the use of blast furnace slag as well as the aggregates for aggregates, chips for pavement construction. Aggregate should be enough. Chemically it should be enough. It doesn't impart any chemical reaction to the concrete structure.
It doesn't impart.
Then it has got some mechanical property. That means it should have a certain limit of Los Angeles abrasion test.
So can you repeat one?
Los Angeles abrasion test.
Yeah.
For abrasion, it should be abrasion resistance. It should be it has got some impact value. As you got the impact value as the material is more, is prone to breaking. So that means it should be within certain impact value. And that one should be water resistance as well. As you got, the indicates for concrete should be at least 1% or 1.5%, the maximum water absorption.
Exactly. The air gap spaces are compromised if the entry kind propagation is large. So the air gap spaces, if they are compromised, there is no allowance for the water to expand to freeze.
And the freezing is occurred only the reason why the temperature below sub-zero.
Yes, sir.
But in case of our areas, the problem of freezing is not so serious. So my question is, all these mechanical properties are conducive for using the blast furnace slag as a pavement, concrete pavement. And because concrete should be dense, that's why pore refinement is more essential than steel.
The last part I did not get. Can you please repeat without the mic? It's different.
Pore refinement. That means dense of the concrete, more of the steel. As because last some few decades we are trying about the strength. We didn't go for any durability. The durability has come into picture. Durability is the check against the failure of concrete by ingress of water within the concrete. So the concrete should be water repellent at least for having durable concrete. But as because corrosion is a very major problem, so after 10 or 15 years, we see that the new concrete is again become brittle. So
yes,
the pore refinement and this ingress of water should be stopped in the concrete. And from that point of view, whether this slag will be prudently be used in concrete making or not.
So the point is, if we are actually using something which is water repellent, then the initial investment in order to construct the concrete pavement or the concrete road increases. So if we are ready to invest that extra amount in order to construct the road, in order to construct the pavement, if we are ready to invest that extra amount, then there can be absolutely nothing better. But what is of more economic significance is we can make the pavement or concrete extremely well drained or well monitored such that the moisture content, because the adhesive property, the cementitious property of the concrete enhances in presence of a certain minimum amount of water. When it gets excess, what it does is it cracks the concrete, it makes it to fail. But if we are making the pavement or construction concrete well drained, or we improve the drainage system of the existing concrete structure.
And because drainage will invite again the intrusion of gases, alkali,
yes, sir.
Your chlorine, these gases are detrimental for corrosion of reinforcement.
Yeah.
That is not advisable. That is not advisable. Draining is not the
Sir, obviously,
process.
as I said, the best process is if we can use water repellent construction material. That's the best process. But if you are actually the construction pavements or the roads which has been constructed till date, they are not made of. They are rarely made out of water repellent material. So the point is, if
not the water repellent, but the question is the aggregates should be water level or it has got very less amount of absorption.
Exactly. So the
Totally water level just got some limit. After that level, it is
saturated.
Alomon, actually first I commend you for such an excellent presentation. I mean, we can't think of in all earlier days giving this kind of presentation. We must clap. And the photograph that you put there, it's representative of you, Alomon. But only one small thing just I wanted to make. You have a good presentation. We are from the steel industry. What I understand that you have been using the word BF slag, BF slag, BF slag. Actually, you know, getting BF slag for road making will be very difficult. It is extensively used for cement manufacturing. Probably the slag that you are trying to refer to is the SMS slag. Might be a little bit difficult for you to understand what is the BF and what is the XML. We create two kinds of slags there in steel melting process. One is the BF slag, which is sold like hot cake. I mean, simply we can't spare even an ounce of BF slag. Just the trucks after trucks are just waiting outside to get the BF slag, whether it is in a granulated form, whether it is in any form. They will take it, they will make cement out of that. But we have a problem in disposing of the steel melting shop slag. We call it BOF slag. BOF is a little bit, only from the steel industry people will be able to, they will be able to understand. Probably, I don't know whether this is the research work that we have done, focusing on BF slag or probably wanted to mean BOF slag. So I will request you next time go back, just check everybody BF slag, fine. So one can do a research on BF slag itself. And probably next time when you are coming up for different presentation, probably you have to change the BF by BOF. That's it. Nothing more. Thank you.
Now, for the information, the BF slag is used, not the BOF slag.
Is it? Okay.
Yes.
Okay. I stand corrected. Okay.
Okay, thank you. See you all over for your